Hi, today we'll explore the major forces acting on an airplane. Every object on Earth is affected by gravity. An object's weight, like that of an airplane, is the result of gravity acting on it. Gravity pulls things toward the center of the Earth, making weight a downward force. To lift anything off the ground, there must be a counteracting force strong enough to overcome its weight. This force is called lift, and it is generated by the airplane's wings. Lift is the result of a pressure difference above and below the wings. This is known as Bernoulli's principle. Air moves faster over the curved upper surface of an airfoil than it does beneath the relatively flat lower surface. So the pressure above the wings is lower than the pressure below. Air, like water, flows from high to low, and pushes the airplane upward. This upward force is lift. It's what allows the airplane to stay in the air. But why? Why does air move faster above the wing? A common explanation is that the air travels a longer distance over the curved upper surface of the wing. So it must move faster to meet the air below at the trailing edge at the same time. However, this explanation is actually incorrect. In reality, the air above the wing reaches the trailing edge earlier than the air below. The true cause is more complex, but we'll focus on two most common explanations. First, there's the continuity principle. As air flows into the leading edge of the wing, some of it is temporarily blocked by the wing. This reduces the air density above the wing. According to the continuity equation, when the density of the air decreases, the speed must increase. You can think of this sudden drop in air density as creating a vacuum effect, which essentially sucks the air toward the trailing edge. Next is angular acceleration. As air moves around the leading edge of the wing, the air goes above the upper surface, experiencing more turns than the air below. The change in direction is a type of acceleration called angular acceleration. Since linear acceleration is proportional to angular acceleration, the air above the wing speeds up. In fact, the wing's upper surface doesn't even need to be curved to generate lift. The angle of attack works similarly to a curved surface. That's why airplanes use a high angle of attack during takeoff and climb. More lift is required during these phases of flight. When the angle of attack increases, air is directed more downward. According to Newton's third law, this downwash of air produces an upward reaction, lifting the airplane. This is another reason why a higher angle of attack is necessary for takeoff and climb. Lift comes with a cost. At the wingtips, the separation between the upper and lower airflows disappears. And air swirls upwards from the high-pressure region below the wing to the low-pressure region above. This creates turbulent vortices that trail behind the wings. These vortices generate drag, a byproduct of the lift produced by the wings. The higher the angle of attack, the greater the induced drag. Other than induced drag, there is another drag acting on an airplane. The Parasite Drag, which is unrelated to lift but due to the airplane's structure. It has three types. Form drag is caused by the protruding components of the airplane disrupting the airflow. Friction drag results from the air's contact with the airplane's surface. Interference drag occurs when air flows over the junctions of different airplane structures, such as near the wing root, creating turbulence and eddies. Drag is the force that pulls the airplane backward, and it's closely tied to the airplane's speed. Parasite drag increases with speed, so the faster you go, the more parasite drag you get. On the flip side, induced drag decreases with speed, which makes sense since it's a byproduct of lift. Less lift means less induced drag. Combining the two drag curves, you get a V-shaped total drag curve. During takeoff and climb, the plane is moving slowly, induced drag takes the lead. As the plane speeds up, parasite drag prevails. The point where total drag is at its lowest is the intersection of induced and parasite drag curves. This is known as the maximum lift-to-drag ratio. The speed at this point is the best glide speed. The force that counters drag is thrust, which is generated by the aircraft's engines through its propulsion system. Along with weight and lift, we have four forces act on the airplane. Any imbalance between these forces will cause the airplane to move in the direction of the stronger force. When the forces are in equilibrium, the airplane maintains a steady and level flight.